Today we're going to look at section 7.6, solving exponential and logarithmic equations. Our objective is to be able to solve equations using the properties of logarithms and to be able to use the change of base formula to solve those equations. We're going to look at 6 equations today, and our goal is to solve for x in each of them. And what makes this problem a little bit harder is that our x is in the exponent. And if this would have been a number, we could have taken the root of that number to both sides. But because it's an x, I'm not allowed to type this in my calculator how I see it. So what I'm going to do is change it to log form. This should be review. I'm going to do log base 2 of 7 is equal to x plus 2. Now, this doesn't have any x's, so that means I could type in my calculator. This is, remember, if I use the change of base formula in my calculator, I would type this in as log of 7, make sure you use parentheses, divided by log of 2. Because if you remember, our calculator only does base 10, and this is base 2, so this is the only way we can do this. If we do this, this is approximately 2.807, and it's going to keep going on. Leave it as this completely in your calculator. Just leave it there. So I'm just going to rewrite that here. Again, it keeps going on. I'm just going to show that with a couple dots. Equals x plus 2. Okay. And then what I need to do is I need to subtract 2 from both sides. And if I do that, I'm just left with the decimal part. So my answer would be, and we're going to round to 3 decimal places today, 0.807 is equal to x. Now, you can substitute that back in. Now, you're not going to get exactly 7 because we rounded, but if you left this completely how you see it in your calculator and substitute back in, you'd see that that is a correct answer. So my answer is 0.807. In example 2, again, I'm trying to solve for my exponent, but what you need to do first is you want to isolate the power that has the x in it. So what I need to do is subtract 5 from both sides first. So I'm going to be left with 10 to the x equals 55. Again, my exponent is the x, so it's hard to solve it in exponential form. So if I change this to log, this is log base 10. Now typically if it has a base 10, we don't write it, of 55 equals x. Now, you're not going to get it wrong if you do write it, but I'm not going to write it just to show you that log 55 is the same thing as log base 10 55. Now, the nice thing about this is I don't have to do any change of base because it has the same base as my calculator. So if I just type log 55 in my calculator, I'm going to round it to 3 decimal places. I get 1.74, and it stays at 0. And if I substitute this back in, again with the whole thing in my calculator, I'm going to get an answer of 60. Our next couple of examples are going to deal with logs. There's a couple of different ways to solve this, but what you want to look at is we have log of 3x. Now 3 is multiplied by x, so I know this whole thing is stuck together. So what I want to do first is divide both sides by 2. There's a couple different ways to do this, but this will probably be the easiest algebraically. Okay, so now again, I cannot type this in my calculator, even though it has an imaginary base 10 because I have an x here and I can't type that in to my calculator and have it solve. So what I'm going to do is I'm just going to put that little 10 here just to remind you, and I'm going to change it actually back to exponential form. So this would be 10, base 10, to the power of 2 is equal to 3x. Now this is something that I can actually solve. I'm going to get 10 squared is 100 equals 3x, and divide both sides by 3. So I'm going to get x is equal to 100 over 3. I'm not going to reduce this. I'm going to actually leave it as a fraction because it's the exact answer. It's always better to have the exact over rounded, so I can leave it like this. My other answers I'm unable to change to a fraction. Now, logs are a little bit special. If you remember, the base value and the of value has to always be positive. And if I substitute this in, I'm going to get exactly 100. So it is positive, so I know this should work. And again, substitute it back in and you'll get 4. In this example, it looks a little bit crazier, and some students get confused by what goes together. I have log base 4 of x plus a log base 4 of x. Now this minus 6 isn't with it. In our last problem we had 3x, and I know those are combined because they're multiplication. This 6 is not part of the log. If it was, I'd have parentheses around the x and the 6, which I do not. So I'm going to keep it like that. The first thing I'm going to do is going to add 6 to both sides. So if I add 6, I get a positive 2. Okay, so now there's a couple of different ways we can do this. If you remember, when you add 2 logs, it's like multiplying these. So I'd get log base 4, x times x is x squared. Another way you could have thought about this is I have log base 4 plus log base 4. Well, they're like terms, so I have 2 log base 4 of x. Well, if that 2 in front could be raised as an exponent, and we get the same result. And this equals 2. Again, I cannot type this in my calculator how I see it, but I can use switch back to exponential form. I have a base 4 to an exponent of 2 equals x squared. I'll write this up here. Now I have 16 is equal to x squared. Hopefully remember to do this. You take the square root of both sides. When I take the square root of both sides, I'm going to have plus or minus 4 is equal to x. But we have to remember, whenever you have a log problem, and we start with a log problem, you have to make sure that the base value and the of value, when we say log base 4 of x, are both positive. Well, the base is already positive because it's 4. But if I substitute a 4 into x, everything's positive. If I substitute a negative 4 into x, it doesn't work. So negative 4 is one of our extraneous solutions, so x equals 4 is my only answer. So you do have to be very careful with log problems in substituting it back in. Now you might think, can I always just get rid of the negative answer? And the answer is no, because sometimes depending on what other numbers are up here, when you substitute in that negative, you still get a positive, which then makes it okay. Alright, so let's look at another example. Well, if you remember, I have log base 6 of x minus log base 6 of 7. If you remember, the property says if you're subtracting logs, we divide our values. So it's the first one is our numerator, our second is my denominator, equals log base 6 of 5. Now if you notice, I have a log of 6 base 6 on both sides. So since the log is already equal to the log, the 6 is already the same as the 6. The only thing that I have to guarantee is the same on both sides to make this equal is the x over 7 and the 5. If those two values are exactly the same, both sides are equivalent. So I can just disregard the log base 6 and just concentrate on this part of the equation. And I'm going to get an answer as x equals 35. Now again, if I substitute 35 back in, all my logs are positive, so x equals 35 is my answer. In our last example, we have log base 5 on both sides, which is a good sign. But I have this 2 in front. And what I'm going to do is use the property which says if you have a lead coefficient, you could be raised as an exponent. So I'm going to rewrite this as log base 5 of x squared equals log base 5 of 10x plus 24. So I'm not going to do anything to the right-hand side. Again, I notice that they both have logs. They both have base 5. So the only thing I have to worry about is as long as these two values are equal, both sides are equal. So now I can write an equation. X squared equals 10x plus 24. And hopefully you remember from our quadratics chapter, we have x squareds and x's. So what I'm going to have to do is move everything to one side. And I prefer to keep my x squareds a positive, which makes this equal to 0. Now, how could you solve this? You could use the quadratic formula. You could complete the square. But the fastest way is to factor if it's possible. And this trinomial does factor. X squared is x times x. 24 is actually 1 times 24, 2 times 12, 3 times 8, 4 times 6. So which of those gives me a 10? Well, two of them do actually, the 6 and the 4, which most students jump to, but also the 12 and 2. And actually the only one that works is 12 and 2. If the 12 is negative and the 2 is positive, they multiply to give me a negative 24, add to give me a negative 10. Using the zero product property, if I set each parenthesis equals 0, I'm going to x equals 12 and x equals negative 2. So again, I need to double check. If I substitute in a 12, this is positive. If I substitute in a 12, that's obviously going to be positive. It's going to be a huge positive number. Now what about a negative? If I substitute a negative 2 here, it does not work. If I substitute a negative 2 in here, I get 10 times negative 2, which is negative 20, plus 24 is actually a positive 4. So you have to check everywhere when you substitute x, because if I substitute on this side, it actually makes this positive, even though the x value is negative, which is okay, but it fails on the left-hand side. So for us in this case, x equals 12 is the only solution that will make both sides equal. Hope you feel a little bit better about solving exponential and logarithmic equations, being able to use the properties of logarithms, and using change of base.